In this video we're going to learn about NumPy, one of the most popular Python modules. NumPy calls itself the fundamental package for scientific computing with Python, which is true. Almost anybody who does any kind of data analysis in Python is using NumPy in one way or another. It's incredibly popular, so it's a good thing to learn, and also the popularity means there's lots of helpful NumPy tutorials and lots of code out there for you to use. NumPy has many different features. There's a link to the documentation in this notebook, and you can read about all of them there. It can do randomization, it can do numerical linear algebra, statistics, plotting, it can work with sets, and even more things. In this video we will just learn about the fundamental NumPy data structure, which is the array, and a little bit about how to do some linear algebra in NumPy. So that we can use NumPy, let's import it on this line here. And the standard way to do that is to import NumPy as NP. That way you can refer to NumPy functions and objects using np.whatever. The most important NumPy object is the array. A one-dimensional array is something which behaves like a list. A two-dimensional array is something which behaves like a matrix or a vector, and you can even have three or higher dimensional arrays. To create an array, you use the command np.array. So in this first code cell, I'm creating a one-dimensional array whose entries are 1 and 2. Each array has a shape. Its shape is a tuple. The size of the tuple tells you how many dimensions the array has, and the entries in the tuple tells you how long the array is along those dimensions. So here, the shape of x is a tuple of length 1, and the entry in that tuple is 2 because x has length 2. Next, let's create some two-dimensional arrays. We'll create a two-dimensional array to represent the 1 by 2 row vector whose entries are 2 and 3. To create two-dimensional arrays, you have to give np.array a list, and the entries of that list have to be lists representing the rows of your two-dimensional array. Here I've given np.array a list, whose element is a single list representing the row 2, 3 of my 1 by 2 row vector. When I ask for v.shape, I get a tuple of length 2 telling me that I've got a 1 by 2 row vector. If you want to create a 2 by 1 column vector, you have to give np.array a list whose entries are lists representing the rows of your column vector. So I should have two lists, one of which contains the entry in the first row and another containing the entry in the second row. This time the shape of my column vector is 2, 1 because this is a 2 by 1 column vector. Finally, to create a matrix, I have to give np.array a list whose entries are lists representing the rows of A. If I want to make the matrix 1, 2, 3, 4, I should give it a list of lists, the first list being a list representing the first row, and the second list being a list representing the second row. This time A.shape is 2, 2, because A is a 2 by 2 matrix. You can access parts of arrays using a similar syntax to how you accessed parts of Python lists. In particular, it's very important to remember that array indexing starts at 0. The top left entry of a 2 by 2 array will be the entry with coordinates 0, 0. If we ask for A1, this will be one of the rows of A, the second row of A, not the first row, the second row, because array indexing starts with 0. If you want the top row, you have to ask for A0. If you want actual entries from A, you need two coordinates to get that. The top left entry has coordinates 0, 0. You can get that either with square brackets 0, 0, or with square brackets 0, square brackets 0. As you can see, that is the top left entry of our matrix A. If we want the entry in the top row and if we want the top right entry, so the entry from the top row at the end, then A01 would do this. And that will be the same as A square brackets 0, square brackets 1. An important thing to remember is that we are representing row vectors and column vectors as two-dimensional arrays. If you want their entries, you have got to give two coordinates. Here W is a 2x1 column vector. If you ask for W square bracket 0, what you get is not a number. That is a one-dimensional array. If you want an entry from W, so a number, then you need to use two coordinates. So to get the row 0, column 0 entry, you use W square bracket 0, square bracket 0, or alternatively, W 0, 0, like this. If you want the entry of W in the bottom row, then array coordinates, as I've said before, work just like matrix coordinates. The first entry tells you the row, the second entry tells you the column. So this would give me the row 1, column 0 entry of W, which is 2, and this will give me an error. Let's correct that. For row 1, column 0, we need W10. A surprising feature of arrays is that you can't check with that two arrays are equal using the double equals symbol. Instead, if you try to use double equals on two arrays, what you'll get is another array telling you where those two arrays were equal. Here I've got a one-dimensional array A with the entries 1, 2, 3, and a one-dimensional array B whose entries are 3, 2, 1. And if I ask A double equals sign B, then I'll get another one-dimensional array of length 3 containing false, true, false, because A and B are not equal at coordinate 0, they are equal at coordinate 1, and they're not equal at coordinate 3. What NumPy has done here is applied double equals to each of the entries of our arrays in turn. This is sometimes called broadcasting. If you actually want to check whether the arrays themselves are equal, you need to use another function called np.array_equal. If we call this on AB, we'll get the answer false that we expect, and if we call it on AA, we'll get the answer true. Two-dimensional arrays behave just like matrices and vectors. In particular, you can add them using the plus symbol and you'll get the answer that you expect. You should contrast that with lists, where you use plus on lists, what you get is a concatenation of those lists. They get joined together. Where you use plus on NumPy arrays, the corresponding coordinates get added just like vectors or matrices. Here I'm adding the two 2x1 column vectors, 1, 2 and 3, 4, and I get the vector addition that I expect. The answer is another 2x1 column vector obtained by adding the first two coordinates and the second two coordinates. You can also do scalar multiplication using the standard syntax for scalar multiplication. Here is a one-dimensional array being scalar multiplied by 2, and you get the one-dimensional array obtained by multiplying all the entries by 2. And here is a 3x1 column vector being scalar multiplied by -1. As you can see, we get the 3x1 column vector obtained by multiplying each of the entries by -1. Another way to do this will be just to write -y. You can also do matrix multiplication in NumPy with the @ symbol. You can even matrix multiply two-dimensional arrays into one-dimensional arrays. If you have a one-dimensional array with a length 2 and a two-dimensional array which is 2 by 2, then you can multiply your two-dimensional array into your one-dimensional array on either side. If you put the one-dimensional array on the right, it will behave like a column vector, and if you put the one-dimensional array on the left, it'll behave like a row vector. So this is just like column vector multiplication, and this is just like row vector multiplication. This might seem convenient, but it can actually lead to all kinds of problems. The reason is, instead of stopping and giving you an error, this multiplication will just continue and give you an answer which may not be the one you were hoping for. Sometimes it can be better if your code actually fails and gives an error, because then you know there was something wrong, and you know where the error occurred as well. It's much easier to fix errors when they happen where you're expecting, rather than somewhere else along the line. So in particular, it's much better to represent row or column vectors as two-dimensional objects in NumPy. Two-dimensional objects must obey the matrix multiplication rules. If you want to multiply an m by n and a p by q array, then you've got to have the number of columns in the first array equal to the number of rows in the second array. In other words, if you're multiplying an m by n and a p by q array, you've got to have n equals p. Let's try that out. We'll multiply here our 2 by 2 array into a 2 by 1 array. That's legitimate, and the answer should be another 2 by 1 array, and it is. Here we're going to multiply a 1 by 2 array, so a row vector, into a 2 by 2 matrix. Again, that's a legitimate matrix multiplication, and the answer will be another 1 by 2 array. We can also multiply a 1 by 2 array into a 2 by 1 array, a row vector into a column vector, and again this is okay. But the answer, you should notice, will be again a 1 by 1 array, so a two-dimensional array, not a number. Finally, let's try an illegal matrix multiplication. If you multiply a 2 by 2 matrix into a 1 by 2 row vector, that's illegal, and you will get an error here. There's a lot of jargon in the error that you get, but you can see at the end that the problem is size 1 is different from 2. It's telling you that you've tried to multiply two matrices or two-dimensional arrays of the wrong shape, so it won't do it. This kind of error is actually good because you see straight away that you've made a mistake by multiplying two things of the wrong size, so you're able to fix whatever error in your code caused this straight away. Let's do a little bit of linear algebra with NumPy. If you want the identity matrix in NumPy, you can generate that easily using np.I. Here I'll get a 3 by 3 identity matrix. You can get a zero matrix in NumPy with np.zeros, and you have to give np.zeros a tuple telling it the shape of the array that you want to create. np.zeros called with the tuple 2, 2 will give me a 2 by 2 two-dimensional array of zeros. You can see that I really needed two sets of brackets in that call to np.zeros because the input is a tuple of length 2. If you give np.zeros a single integer, you'll get a one-dimensional array like this. Another thing to be careful of in NumPy is that you can't compute matrix powers using the same double star notation that you use to create powers of a number. Instead, if you have a two-dimensional array, like 1, 1, 1, 1, and you try to square it using a star star 2, what NumPy will do instead is square each element of a in turn. That's not the same as the square of the matrix AA. Instead, there's a special function for computing matrix powers, which is np.linalg.matrix_power. Here I've created the two-dimensional array 1, 1, 1, 1, and I'm creating its square with np.linalg.matrixPower a, 2. You can see that really is the matrix square of 1, 1, 1, 1. On the other hand, if I try to square it using the double star operator, it won't work. I get 1, 1, 1, 1 again because what NumPy has done is squared each element of a in turn. That's probably not what you wanted, so you have to be careful when you're computing powers using in NumPy. np.linalg.matrixPower can also be used to compute matrix inverses, just by giving it the power -1. Here I have the 2 by 2 array 1, 2, 2, 1, and I ask for its inverse using np.linalg.matrix_power a -1. So that's asking for the -1th power of a, in other words, the inverse of a. We'll check that it's worked by matrix multiplying a by the thing that I've called a inverse. You can see I got the identity matrix, so a_inverse really was the inverse to the matrix A. Determinants in NumPy can be computed using np.linalg.det. Here we should get 3, but we actually get something very, very close. We should get -3, but we actually get something very, very close to -3 just because of a rounding error. You can also compute eigenvectors and eigenvalues, although the command is a little cumbersome to use. If we create the np.array representing the 2 by 2 matrix 1, 1, 1, 1, then you can get eigenvalues and eigenvectors using np.linalg.eig. If you assign that to a variable e, then e0 will be a one-dimensional array containing the eigenvalues of a, and e^1 will be a two-dimensional array whose columns are the eigenvectors of a, but those eigenvectors get scaled so that they have length 1. So here the first output there, e^0, is a one-dimensional array listing the eigenvalues of a. And those eigenvalues, you will remember from an example in 0005, are 2 and 0. The columns of the second array are the eigenvectors of a scaled so that they have length 1. The 0th column corresponds to the 0th eigenvalue in e^0, and the next column corresponds to the next eigenvalue 1. One final useful command in NumPy is linspace. np.linspace computes equally spaced points of a specified number starting at a particular place and finishing at another place. Specifically, np.linspace start stop n produces an array, a one-dimensional array of n equally spaced points starting at start and ending at stop, and including the start point and the stop point. Here, if I ask for np.linspace0111, I will get a one-dimensional array with 11 equally spaced points beginning at 0 and ending at 1. You can see that's what happens. And just to emphasize that this contains the start point and it contains the stop point. So it's not like a Python range command, for example. NP arrays can be treated just like lists in the sense that they are iterable. You can use for loops over the entries of an np.array. Here I'm going to print out each of the entries in the linspace array I just created. You can also use them in list comprehensions. That's going to be very useful to us when we want to do plotting in the next video, because we can use linspaces to create lists of x coordinates and then use list comprehensions to obtain y coordinates. In fact, there's an even easier way to do that. So here is my collection of y's. Let's just print them out. Those are the squares of the entries we just created. But in NumPy, you could even do this just by doing, let's make a variable called x is to hold my equally spaced points, and we'll now do y's equals x's squared. That annoying feature that the double star operator didn't behave as we expected now becomes useful, because now y's is the array whose entries are obtained by squaring each of the entries from the x's.